Good afternoon, everyone. Thank you for being here. Each spring, the Center for Communicable Disease Dynamics hosts its annual seminar series, bringing together experts that share the latest research in infectious disease and epidemiology and modeling. Today, we're pleased to welcome Dr. Paul Zivich, an assistant professor in the Department of Epidemiology at the University of North Carolina, Chapel Hill. Dr. Zivich's research focuses on causal inference with potential outcomes and the computational aspects of epidemiology. His work spans a wide range of topics, including fusion study designs, simulation-based evaluation of estimators, development of free and open source software, and the use of electronic sensors for contact network data collection. He also applies causal inference methods to infectious disease and social epidemiology. Please join me in welcoming Dr. Paul Zivich.
Thank you for the introduction. So my name is Paul Zivich. Title of my presentation is Effects of Influenza Vaccination Among University Students Using Targeted Maximum Likelihood for Interference. So just a bit about who I am. So I lived in Ohio, around the Cleveland area. And then I did my BS, and MPH at Ohio State. Then I moved to North Carolina to do my PhD, where I stayed and did my postdoc and am now an assistant professor there. My research covers a lot of different topics. So today we're going to talk a little bit about interference, but I just want to highlight some of the other things I work on. So I do a lot of work in causal inference. Yeah.
Sorry, can you go back?
Yeah.
To the last slide. I'll try now. Okay.
Great. So I do a lot of work in causal inference on identification problems, right? So writing parameters in terms of our observed data. Also do a lot of work on implementing G methods in different contexts. My applied research is mostly in infectious disease. I used to do a lot of work on respiratory infections, but currently I do more work in HIV. And then I also do some work on fusion designs, which is combining different data sets together, including some work on synthesis modeling, which is connecting more traditional statistical methods with mathematical models. I also do a lot of work in software, including mostly in Python, and these days mostly on estimating equations. So just some brief acknowledgments. This present,
One more time. Okay.
So this presentation is built from parts of my dissertation. So I just want to list my dissertation committee here. And then currently I am funded via KO1, but at the time of this work I was funded on a T32 training grant listed here. A standard disclaimer, you can blame me for any errors. And then if you don't have time to ask questions today, feel free to email me or contact me via any of these other methods. Also, if you have questions as we go through this presentation, please feel free to interrupt me. Don't save your question on slide 5 till the end. And then finally, footnotes are for asides or references, but you are free to ask questions or more details about them. All right, so this presentation is built from these two kind of background papers. So the first is what I recommended as a journal club reading. It's kind of just to set the stage and doesn't quite directly cover what we'll talk about today. And then the second paper is a more stats-heavy paper about how to apply the method that I'm going to talk through today. So unlike that stats paper, I'm going to talk through a motivating example. So we're going to talk about influenza. So influenza prevention is important among university students. Here I'm thinking about undergraduate and university students. So why are they an important population? So university students have an elevated risk of infection, probably because of how close they live in dorms and how they interact in classes, and et cetera. They also tend to have very low vaccination rates. And there's other prior research that indicates undergraduate students are particularly important for further transmission of influenza. So a key preventive strategy for influenza is vaccination. And prior research in university students and influenza has focused on one of two things. One is the direct or unit treatment effect of vaccination, which we'll define a little bit more precisely later, or they have focused on vaccination uptake as the outcome. So I'm going to argue very briefly that this prior research is limited in its public health utility. So regarding the direct effect of vaccination, the direct effect is the expected change of switching a single student's vaccination status in the population, right? So this is a very small scale change in the vaccination rate we're making. And I would make the case that that parameter is less informative for what we're interested in public health. More often, we're more interested in larger changes in vaccination uptake, right? What if we could increase vaccination from 40% to 60%, right? That's much further away from that change of a single unit in our population. Regarding uptake as the outcome, there's a lot of research on strategies to increase influenza vaccination uptake, and that is important research to know what increases or gets people to get vaccinated. But for preventing influenza, the thing we're trying to do, two things are important. One is the extent of uptake, but it's also how uptake is distributed in the population. So you can imagine the case that we have two strategies to increase influenza vaccination rates in the population, but they do so in different ways. And while they look the same and increase vaccination the same rate, one could be more effective at preventing influenza infections than the other, just because of who it gets to be vaccinated and where they exist in that network of connections. So, okay, the question that I'm going to try to address today in this presentation and address some of this prior research is the question is, what would the risk of influenza infection be under plans that increase the probability of influenza vaccination uptake among university students at Midwest University from January to April in 2013. The data I'm going to use to address this question comes from the X-Flu cluster randomized trial, and we're going to use 454 participants from that study. In the original trial, students were randomized to 3-day self-isolation if they had influenza-like illness. We're not going to comment or talk about that aspect. We're just going to focus on vaccination in that study. But the study has 10 weeks of follow-up, and they collected a variety of information on vaccination, risk factors for respiratory infections, and then a bunch of details on respiratory infections, including influenza-like illness, and then laboratory confirmation. And importantly for our aspect is they also collected contacts between students. So this is just a visualization from the first week of the study that shows students' self-reported contacts with other participants of the study. Here I've just colored the nodes by vaccination status. So blue is vaccinated, red is unvaccinated, and then gray is missing. So that's just to give you a general idea of the structure of the network. So the types of policies or shifts that we're going to talk about is we're going to shift that probability of vaccination. And here I'm going to tell a story. We're going to consider 3 kind of hypothetical interventions that address common reasons for not receiving the influenza vaccine. So the first is what I'm going to refer to as like educational policies or plans. And those are intended to correct misconceptions about influenza. So, the vaccine gives you influenza, or I don't need the influenza vaccine. The second are non-financial barriers. So you can think about like ease or the accessibility of the vaccine, right? Are the clinic hours convenient? Those kind of features. And then the last are financial barriers. So maybe less important now, but reducing some of the monetary costs if not when it wasn't always covered by insurance. So the plans we're going to talk about are going to shift the probability of being vaccinated, and they're going to be based on students' self-reported reasons for not getting the vaccine. So it's going to fit in one of those 3 policies, then we're going to shift those probabilities. And importantly for our policies, we're also never going to vaccinate anyone who had contraindications. So our plans aren't going to shift their probabilities. It's always going to still be 0. So there's a variety of challenges. I have 4 here. One is that the vaccination of one student affects whether another can become infected with influenza, right? The spillover effect. Then we have missing vaccination data, as we kind of saw in the network. There's also problems of measurement error of contacts, right? We asked these students to self-report who they had contact with in the previous week, but can you remember everyone you had contact with in the previous week? Probably not, so there's some measurement error. And then there's a bigger problem that we're only partially observing a much larger network. But I'm going to ignore those last 3 issues, and today we're just going to talk about the first, and that's going to be focusing on this kind of spillover interference aspect. So I'm going to start by defining our parameters. To do that, I'm going to introduce some notation. So I'm going to use Y to indicate the observed outcome, and in this case, it's just going to be influenza infection. And I'll use a subscript to denote what person or unit it is. So Y sub I is just the outcome for unit I. A will be our observed action, which in this case is getting the influenza vaccine, again with subscripts. I'm going to use that fancy script A just to denote the support of A. So since we're thinking about the influenza vaccine here, it's either vaccinated or unvaccinated, so it's 0, 1. And then I'm going to use that bold A to just indicate a vector of everyone in our population's vaccination status. W will be a vector of covariates. I'm going to use, again, that fancy script to denote the support or possible values W can take. And then the bold W to indicate the vector of everyone's covariates. And then I'll use that bottom G to indicate our adjacency matrix. So that's just our network expressed in terms of a matrix. So in this case, a 1 in the matrix indicates there's a connection between I and J that is capable of influenza transmission, whereas it would be 0 otherwise. So in our case, we can think about the contact network indicating 2 people who are in close physical contact that influenza could spread. And here, the diagonal or unit I's connection with itself is always going to be 0, because interference is this relation between 2 units. So to define our parameters, I'm going to use potential outcomes. So here I have the potential outcome for unit I, and their potential outcome is a function of the vaccination status of everyone in the population. So we can write it as that bold A. Alternatively, as that equality suggests, right, their potential outcome depends on the vaccination status of all of the other N units. And then as a shorthand, I'm going to use this other expression where I have A sub I, which is the vaccination status for unit I, and then A sub minus I, which is the vaccination status for everyone but unit I. So just a kind of convenient expression. So the potential outcome represents what the outcome unit I would have if everyone had been set according to that bold A. So you can imagine setting A equal to 1 for everyone, everyone's vaccinated, that person would have that potential outcome under that. Most of the time in causal inference, people start off by saying they assume no interference. What that means is this bottom statement here, where we're just saying that A subscript minus I is we can drop it freely, right? Other people's vaccination status or actions don't depend for anyone else. So just continuing with no interference for a moment, right? Often people talk about the average causal effect in causal inference, which is just this contrast here. So we're comparing what if everyone got A equals 1 versus what if everyone got A equals 0, right? So what if everyone in our population took the action or got vaccinated versus not. But we can also generalize this a bit further to what I'll call stochastic plans, and that's what that bottom expectation indicates. So in this case, we're just imagining some policy that's set by you, the investigator, which I'm indicating here by that probability star. And then we're going to see what outcomes would have been like had everyone in that population had their A's set according to that PR star plan, right? So you can think about this as just a generalization, right? If I think about a PR star that set everyone's A equal to 1 in our population, that just becomes a 1 for everyone. When little a is 1, so it just becomes that top part, right? So that's the connection. So this is just a generalization between those. So when we have interference, we need to talk about that minus I. So I have two parameters here that in the case if we say there's no interference, they're actually both just the average causal effect. But with interference, there's an important distinction. The first is the direct effect, which in that case, we are just changing unit I's vaccination status, but we're holding the rest of the population's vaccination status fixed to some level, right? So this is the direct effect. We're just looking at what happens if you change a single unit in our population. What's that expected change? The bottom, we have these bold 1s and 0s, which are meant to indicate that we're setting everyone's vaccination status to 1 versus setting everyone's vaccination status to 0, right? So this is where that direct effect or overall effect distinction comes up. And I would argue a lot of the times in public health, we're interested in something more like the bottom, where we're making these large-scale changes. In our case, maybe for vaccination, we're not really interested in what if everyone got vaccinated versus no one got vaccinated. So the parameter we're going to talk about is this one here, denoted by psi. So we're going to say given an n units that are situated in network G, our parameter is this thing. And what it means is it's just the expected mean or incident proportion of the outcome if the actions of everyone in our population had been set according to this stochastic plan or that probability star. And we're also going to say it's going to hold the network structure fixed and bold W. So that's what that conditioning bar, this W to the right of the conditioning bar means. It just means that W in the population is being held fixed in our network. So how would you interpret this parameter? So how we would interpret size, we would say under the hypothetical vaccination plan PR star, the incidence of influenza would have been psi among the X-flu participants in our study. So now moving to identification. So this problem is hard. Learning the potential outcomes for a bold vector of A is very difficult because there's 2 to the n unique potential outcomes for deterministic outcomes. But our network offers us a little bit of help here in that only units that are connected in the network can have some sort of interference with each other. So that's going to shrink that size of that bold A. If 2 nodes could not reach each other in a network, they can't interfere with each other, so it simplifies the problem a little bit. But it's still very challenging. So we're going to make a further restriction, and I'm going to refer to it as weak dependence. And what that is we have this larger network, but we're just going to say that for unit I, the only people that are important or that can interfere with their outcome are their direct contacts, right? So this is just saying that my vaccination status matters for whether I get flu and also my direct contacts. My friend's friend is not important under this assumption. So that's better and narrows down everything a little bit, but it's still a challenging task. So we're going to rely on a parametric mapping of individuals' direct contacts. So what that's allow us to go from is that whole potential outcome defined by that bold A, or everyone's vaccination status. So just this A subscript I and A subscript I superscript S, where A superscript S is just a parametric map of I's direct contacts. So it's just some kind of generic or general covariate mapping of a person's direct contacts. I'm going to say throughout this presentation that we are choosing the correct parametric map And I'm going to keep it general and not tell you what it is. But in practice, you need to choose something specific. And then we need to assume that that parametric map is correct. So to help kind of get across the idea of what this parametric map is, these are just a few examples. So one is we could just count up the direct contacts for unit I and see what their values of X were and just add them together, right? So this would be like how many of your immediate contacts are vaccinated. If I have 3 of my contacts are vaccinated, that would just be a 3. We can also think about doing the mean, where we're just dividing by the count version by their total number of contacts, right? So it's just some proportion between 0 and 1. We can also think about thresholds. So you can think about, do you have at least this many vaccinated contacts? We can also get more complicated and do vectors of thresholds, right? So here I just have a bunch of different threshold values, and we're just going to do a whole vector of them. These are just some examples, but the point is that's what's going to underlie all of that superscript notation, and we're going to believe that we've chosen the correct parametric map hereafter. All right. So with those extra pieces, we can now simplify our parameter. So we have psi is now just this potential outcome is just with A and A superscript S. And then our plan, we only need to talk about A and A superscript S. So we've simplified things a little bit. One thing I'll note is plans that are specified like this are pretty hard to think about. Usually we think about something more like this, where we're just saying that we're setting an individual's vaccination status according to some probability. I'm not necessarily thinking about their neighbors at the same time. But we'll see later on how you can use this probability to get back to this joint probability up there. So there's some identification assumptions. Oh, yeah.
Okay, so I know we're taking an expectation over stochasticity in the plan.
Mm-hmm.
Should we be understanding that we're taking an expectation over some data, stochastic data generating process for yi, or how should we be thinking about that?
So the way that I find helpful to think about this is we are looking at all the different possible plans. So like if we forget about interference for a second and just think about a binary outcome, right, there's 2 potential outcomes and we're just taking a weighted average of those 2. This idea is just generalizing it to now it's more complicated because we need to summarize over all of the combinations. The expectation here, as we'll kind of see when we come back to the inferential model, is I find helpful to think about as like an outcome model, right? So we're going to imagine that we have not just one network, but we're going to have a population of networks that are all just an infinite number of copies. And we're going to apply this plan to each of those networks. And then the outbreak or whatever is going to happen. And then we're going to calculate the mean in each of those networks. And then we're going to average those means together. So that's what this expectation and then taking the average of that expectation is meant to capture. So identification assumptions. These will kind of look familiar, but they're extended a little bit to account for this A superscript S piece. So now we have causal consistency, which is just a link between our observed outcomes and potential outcomes. So rather than just saying that we need individual I's vaccination status to link their observed and potential outcomes, we also need their contacts summary of their vaccination status. For exchangeability, so now we need both A and that A superscript S to be independent of the potential outcomes given W and some summary measure of your contacts confounders. And then positivity, because we're thinking about stochastic or probabilistic plans, we just need that anywhere our plan says you have a non-zero probability of that pattern of vaccination among you and your contacts, that pattern also has to have a non-zero probability in our data. So before I had mentioned those contraindications, so if we try to vaccinate those individuals with contraindications, that's when this positivity assumption will become a problematic. So that's why we're not going to try to vaccinate the individual with contraindications. So in our example, the covariates I'm going to include in W are gender, race, stress, optimal hand hygiene, high-risk conditions, sleep quality, alcohol use, trial arm, and number of unique contacts. For the sake of the presentation, I'm just going to say that these are true, right? Those are the sufficient confounding set. And then I'm going to assume some covariate mapping, shown here. The one that we'll talk more about is vaccination, and we're just going to say the correct summary measure is a count. So it's just a count of how many of your direct contacts are vaccinated. Yes?
Could you just explain for some of the covariates like optimal hand hygiene, sleep quality, are those related to getting vaccinated?
Yeah, so we included them in the model so in their relation to vaccination, their general kind of health habits, right, or healthy habits. So we think that is on the path from some unmeasured, health behavior kind of construct. Relates to those, it relates to vaccination. So we're trying to account for healthy behaviors through those kind of variables. Yes, so then moving to estimation. Yeah.
I know you mentioned in that previous slide, but I didn't understand the one that you decided to use count for vaccination rather than the proportion of your contacts.
Yeah. So in some other simulation work, it seems count tends to work well, and you can model flexibly. The thing that we have here is I also am including number of unique contacts in the model. So if we're modeling both of those, it can capture also that proportion. So that's why we're doing counts here. All right, so how do we estimate this parameter? So if you've used targeted maximum likelihood estimation or TMLE in the case of independent and identically distributed data, this kind of 5-step process is probably going to look familiar, right? We're going to fit some nuisance models for different processes. We're going to put them together via a targeting model. We're going to compute some, yeah.
I think it's fair to guess that a small fraction of the group in this room has done this.
Oh, don't worry. We're going to go through the complex version. I'm just outlining the steps. Don't worry. So we are going to compute predictions and then do our inference via the influence function. So same idea from the ID independent and identically distributed data is also going to carry over to our network data. So step one is we're going to fit an outcome nuisance model. So to do this, I'm going to have in my data set, I'm going to calculate, I have A and W measured, and then I'm going to calculate my summary measure A superscript S and all of my W superscript S's from the network and A and W. And then I'm going to treat those observations as if they are independent, and I'm just going to fit a model for our outcome given those variables, right? So in our case, you just fit a logistic regression model for whether someone had an influenza at week 10, yes or no, by all of these other covariates. Nothing special here. Then using that model, we're going to generate predicted values from that model, which I'm just going to denote as y hat. Step two is to get our inverse probability weights or do this action nuisance model. So for the targeting step, we need this probability, inverse probability weight here, which I'm just going to write as shorthand of pi star over pi. So if you remember, we're setting, or I said we're setting PR star. The bottom we need to estimate. So for the denominator, we can factor this into two parts. We have the probability of A given W and WS, and then the times the probability of A superscript S given A, W, and W superscript S. So again, we're just going to treat our observations as independent and fit standard regression models. So as I said before, I'm going to treat vaccination as a count. So for modeling that, I'm going to fit this pair of models here. The first model is just a logistic regression model that has W and W superscript S. For the second model, we're just going to fit a Poisson model that has A, W, and W superscript S, right? So nothing nothing too crazy. For the numerator, I said we tend to think about our policies like this. We're setting an individual's probability of being vaccinated, not really thinking about their probability of being vaccinated and patterns of their contacts. So it gets a little hard to think about that. So one easy way to get that pi star, this quantity, is we can use this Monte Carlo procedure. So first thing we're going to do is create a copy of our data. Then we're going to set A according to some plan, and according to our plan, and then have that as A and A star and AS star. Create a bunch of copies. We're going to do this a bunch of times. K, I'm going to make it 100. And then we're going to fit models for that, much like we did for the denominator. And then I'm going to use those models to just predict using my observed values of A. So a targeting step is just a intercept-only logistic regression model where we have the predicted value from step 1, that predicted outcome, as an offset. And this model is going to be weighted by those probabilities that we just calculated. And that is going to, you can think about this eta as a sort of correction factor if we're thinking about double robustness. The idea is when our outcome model is wrong, but the weights are right, we're kind of adjusting our outcome model predictions by that eta. So once we have that, we can estimate our parameter of interest using another Monte Carlo procedure. So we're going to set our actions according to that plan that we talked about. Then we can compute a predicted value of our outcome, y hat star, using those set values of A. We can then update our outcome using that targeting model step. And then we're going to take the mean. And then we're going to do that 3-step process k different times and get k different size. And then we're going to average those all together. So for inference, as I kind of suggested earlier, we're going to imagine we have a bunch of exact copies of the network. So they have the same exact structure. We're also going to assume or say that they have the exact same values of W. And we're going to apply our plan to all of those networks. And the average of those averages in the networks are going to be what psi represents. So the nice thing about TeamLE in this context is it gives us an easy-to-use variance estimator. Mainly, it uses this influence function. We're going to use this bottom one, which is just going to account for some dependence between our observations. All right, so moving to the yes.
So I often really struggle with thinking about
Yeah.
crosswalks between traditional transmission dynamic models and these kinds of linear logistic regressions.
Yeah.
So I'm curious, is there a good crosswalk to understand when you define this counterfactual? Like, can you define what that counterfactual is on sort of the agent-based model we might have in our heads?
I think so, yes, because we can simulate data according to those models. So I think there is a way to kind of go back and forth. So I found helpful when working on this to designing like the simulation study or simulating observations according to these models was helpful for me to understand what they kind of implied. So yes, I think there is a way you can kind of connect the two. I think, with an SIR model, right, the mechanism of transmission is a little different than how this model's assuming the world works, right? So you're not specifying in the same way. So there is a bit of a distinction in that.
I guess what I often struggle with is there a risk that the counterfactual this proposes wouldn't fall naturally in a transmission dynamic framework? Like, are there any ways that we're sure the constraints that we think are mechanistically true get pulled through this model?
Yeah. So one issue, right, is that weak dependence assumption that we're making. That isn't necessarily going to be true in some of these longer chain models, but what we can do is we can divide time into shorter chunks, which may make it more reasonable. Ultimately, I think the assumption that's doing a lot of work is that parametric mapping, right? that parametric mapping, I think, is what allows the connection between the two. So it all comes back to whether you believe that there is a parametric mapping that we could have that summarizes context. Yeah. All right, so just as a brief reminder, right, we have these three categories of policies: educational, non-financial, financial policies. So this is just a quick summary of the data. Fairly common influenza-like illness, less common laboratory-confirmed influenza, not too much vaccination, but also a fair bit of missingness. And then these are the amount of people that will be targeted by each of the policies. So our policies are just we're going to estimate this probability of A equals 1 for every unit given their covariates, and then we're going to shift those values. So the policy I'm thinking about here is if a student self-reported the reason our policy was targeting them, they're getting shifted by omega. Whereas in what I'm going to present today, we're also going to shift even those who didn't get targeted by the policy, but just by a lesser extent. And we're going to explore this range of values. So I don't know what of these is the most reasonable for our policy, so we're just going to explore a range. So this is what we're doing, is this gray is our observed distribution of the estimated probabilities, and then these are just the three different shifts according to our policies. There's other systematic errors. For the interest of time, I'll just note that we used mice and then some stochastic block modeling to try to correct for measurement error. These are the results. Maybe not super exciting since everything largely overlaps, but in the top plot, we have influenza-like illness. This y-axis is the incidence proportion, and then the x-axis is our shift in the log odds of vaccination. So we can see there's a large difference in risk between influenza-like illness and laboratory confirmed, and we see as you increase the log odds of vaccine according to the policy, generally both tend to go kind of downward, but we're very imprecise in this setting. And also the policies all look very similar to each other. So we don't see a lot of distinction, especially with the amount of random error we have. So to wrap up with some conclusions, interference is common in infectious disease epidemiology, as I'm sure you all know, and it modifies how we should view our parameters, right? That distinction between the direct effect and overall effect. And we should try to consider what is most meaningful for public health. So in this work, I tried to focus on a relevant public health question and using some modern kind of causal inference approaches to address that motivating question. There's a lot of different practical challenges. For the interest of time, I'm just going to skim them over. One is weak dependence, which is that your immediate contacts are the only ones that are important. Over 10 weeks of influenza, probably not too reasonable of an assumption. But what we can do to get around that assumption is you can imagine a longitudinal extension of TMLE, such that each of the weeks we think about time unit is 1 week. And under that weak dependence assumption becomes a little bit more believable, right? You're probably not going to have a long chain of transmission for influenza over a week. There's also interest, as I kind of mentioned, these covariate mappings, particularly strong assumptions. So what are ways that we can get around it or more flexibly avoid that? And then I think also comparing against alternative approaches. So I have not done it, but Eric Chechen has this auto-G computation that's built in a very different way. So how do those two relate to each other, and what's the trade-offs between the two? These are some further readings if you want some more of the theory behind these estimators. And then, so thank you. I'll take any questions. I think we have some time. And then if you want to contact me, feel free to reach out through any of those routes. If you want to know more how to implement it, because I went through everything pretty quickly, there's more details in this 2022 paper.
Thanks. So in thinking about how to approach a question could, as Alyssa was kind of alluding to, you could just estimate some parameters either externally or from your data, and then run a full individual based model that makes your most realistic guess.
Yep.
And that's some Monte Carlo process, and this is Monte Carlo.
Yep.
So what are the pros and cons of?
Yeah, that is a great question. So I think an advantage of taking this approach is that our outcome model is based on the data we actually got to see. If we wanted to build that agent-based model, right, we have to get parameters usually from somewhere external. Not always, but usually a lot of them come external. In using those parameters, we have to assume that they kind of transport directly, right? So I think, that could be a bit of a leap in some context. So I know there was some work on hand hygiene I did, a review, and a few of the modeling studies used children's face touching habits to extrapolate to adults, right? And there's probably an important distinction between those two. So, are these parameters transportable? I think the advantage of this approach is that you're using the data you have to estimate those things. The other piece is, I think, the double robustness offered. We have these two different models. One is for our outcome process, which I think is shared across both approaches. Just how they model it may be a little bit different. But TMLE also has that vaccination model that I don't know functions I don't think it functions in the same double robustness way in the ABM kind of literature, right? So that, in our case, we have two models we're estimating, and we just need to get one of them right. Yes, so we could have the outcome model wrong, but as long as that action nuisance model and our weights are correct, we're going to get the correct answer. Correct point estimate. Our variance is going to be larger than it need be, but that's, maybe okay.
So you mentioned about double robustness, but I wonder, which part in this TMLE procedure kind of, gives the advantage of TMLE applying to this kind of data just compared to, a double robust model, more efficient, but, which part of the TMLE kind of less efficient?
Yeah, so I think a lot of the original work in this area, right, comes from Mark Vanderland's group. So they present everything in terms of TMLE, but you could also reframe all of this work in terms of an AIPW estimator. So either is fine. TMLE has some bounding guarantees, which are nice, but either will bring along that double robustness. For me, at least, the main advantage of using TMLE, so when we went through this three-step process, this is the G computation estimator, this is our IPW estimator, and you can do either of those and get a point estimate. The hard part is when it comes to inference. There's not a straightforward way to bootstrap this data. So the advantage of something like TMLE or AIPW is it gives us a way or a few ways to estimate the variance. So I think that's the main advantage.
Maybe I missed this, but what is the percentage of the students in your university that were included in the study? And I have trouble understanding how everyone else that they may come in contact with who were not in the study, even beyond the week dependent assumption, how all of those potential sources of infection are taken into account.
Yeah, that is a great question. So it is a very small proportion of the overall student body. I don't know the percentage, but they were students living in one of 6 dorms, and they tried to recruit students based on certain structural features of the dorms and used some respondent-driven sampling. So we don't have the full network. So the question is, because we don't have that full network, what happens to the people outside of it? And that is somewhat of still an open question. So I would say that it's arguably assuming some sort of random contact with other people outside of the study under some unknown pattern, right? Just as kind of an outside force of infection. But I don't think there's been any work, formal theoretical work on what happens if you just have a subset of that network, right? So for the purposes here, we're pretending that's the whole network, but not really true.
We have one more question online, and then we unfortunately have to wrap this up. So the question is, was there any evidence of associativity in the network with respect to the reasons people didn't get vaccinated?
That is a great question. So I did not look at for the assortativity of reasons, but I was curious if vaccination was, and there was no assortativity by vaccination, which I was a little surprised by in the network. But I did not look at for the reasons for not being vaccinated. That's interesting, and I'll have to go back and look at that.
Okay, I think that's all the time we have today.
Thank you.